Hi. In this video, we'll look at derivative shortcuts for the rest of the trig functions. So we already saw the derivatives of sine of x and cosine of x. So we'll see the other four. That is the derivative of tangent, secant, cosecant, and cotangent. So you can find all these in the book, but here are the derivative rules for these four trig functions. And actually, all four of these we can derive using the quotient rule. So I'll show you an example of doing one of them, and you can look in the book for others. So to talk about the derivative of the secant function, we'll start by remembering that secant is defined to be the reciprocal of the cosine function. That is, secant is 1 over cosine. So the derivative of the secant function is the derivative of 1 over cosine, and we can use the quotient rule to find the derivative. So we have that the derivative of 1 over cosine is sine of x over cosine squared. We can split up that cosine squared to be cosine times cosine. And then we can recognize this as the product of two fractions, 1 over cosine x, also known as secant x, and sine over cosine x, also known as tangent x. So we conclude the derivative of secant is secant x times tangent x. Of course, this is when the denominator is not 0, so when cosine is not equal to 0, which is also the domain of the original secant function. So let's put some of these to work. I would like to see evidence that the function tan x is always increasing. So why is the tangent function always increasing? Well, remember that a function is increasing exactly when its derivative is positive. So let's see that the derivative of tangent x is always positive. And there's not any work to do here. We know that the derivative of tangent is secant squared. Remember, we write these squareds next to the name of the function, even though we mean secant x times secant x. It just removes any confusion that we're not writing secant of x squared if we wrote secant x squared. So the fact that we're squaring this thing means it can never be negative. Right? If secant x were negative, it would be a negative times a negative. We'd get a positive. And it turns out it can't be 0 either. Remember, secant is 1 over cosine, and 1 over cosine is never equal to 0 because there's a 1 in the numerator. So we're done. The derivative of tangent is always a positive number, and that is to say that tangent itself is always an increasing function. Well, everywhere in its domain. I encourage you to take a look at a graph and see that that's true. Next question. When does the function secant of x have a horizontal tangent line? And well, hopefully we see horizontal tangent line and immediately our minds jump to derivative equals 0. So we can rephrase this question. When is the derivative of secant x equal to 0? So again, there's not any real work to do here. We know the derivative of secant x is secant times tangent. So when is that equal to 0? Well, there's two factors. Either the first factor is 0 or the second is 0. When is secant of x equal to 0? We just said above, never. So that will never contribute a solution. How about when is tangent equal to 0? Well, tangent is sine over cosine, and a fraction is equal to 0 when its numerator is equal to 0. So when sine of x is equal to 0. And that happens at all the multiples of pi. 0, pi, 2 pi, all the positive multiples, as well as minus pi and all the negative multiples. Okay, and one more. Let's consider this function f of x, which is 2x squared tan x over secant x. And I'd like to know what's the derivative at pi. What is f prime of pi? Now notice here, this is obviously a quotient, so we'll need to use the quotient rule. But in the numerator, we actually have a product of two things. It's not just plain old 2x squared, which we could handle easily, or tangent x, again, which we can handle easily. It's the product of the two of them. So as part of applying the quotient rule, when we take the derivative of the numerator, we'll have to apply the product rule too. So this is a good example to see, which makes it a longer question, but not really a harder question as long as we are careful here. So f prime of x, applying the quotient rule, we might write something like this. Here I've left in this operator d dx to remind us of the things we still need to differentiate. So we can take the derivative of that first piece, the numerator, carefully using the product rule. So 2x squared times the derivative of tangent plus the derivative of 2x squared times tangent. Derivative of secant, of course, secant tangent, that's one of the new rules we just learned. And we could leave it like that. I will distribute on the top here, collect our factors of secant and tangent, and it looks like a doozy. So what is f prime of pi? And if you look through here, we only need to know pi. We only need to know a few functions evaluated at pi, that is secant and tangent. So let's remind ourselves, what is secant, what is tangent, what are their values at pi? And we see secant of pi is minus 1, tangent of pi is 0. That'll be really helpful. So some of these terms will just disappear. And if we plug them in carefully, we'll see f prime of pi looks like this. Cancel out the terms that are equal to 0. Minus 1 squared is 1. Minus 1 cubed is minus 1. And the answer, minus 2 pi squared, which is about negative 19 something.